Jai Hind and good morning. I am Professor Devendra Singh, and today I am going to discuss about the third part of the elastic constants. In last two lectures, we have discussed the derivations or establishing the relation between the modulus of elasticity, modulus of rigidity, Poisson ratio, and bulk modulus. So we have derived E is equals to 2g 1 plus nu E is equals to 3k 1 minus 2 nu. Nu is the Poisson ratio. That relation we have discussed. In this lecture, we will discuss the relationship between Eg and K. E is the modulus of elasticity and G is the modulus of rigidity and K is the bulk modulus. And then we will try to attempt some numerical problems to determine the values of these elastic constants. So, the relationship between Eg and K, the basic relation we have already derived, that is E is equals to 2g 1 plus nu and E is equals to 3k 1 minus 2 nu. That two relations we have derived in our last two lectures. Here, for the derivation, what we will do, we will just find out the value of nu from each of these two relations, and for any material, Poisson ratio is a property or this is elastic constant for a particular material. So, it must be same for the same material. Then we will equate the values of nu and we will get the desired relationship between Eg and K. So, that I have already written there. These are the two relations I have derived. So, from these two equations, we should try to get the value of nu. From this side, E upon 2g minus 1 is equals to nu, and nu is equals to E minus 2g upon 2g. This is just a mathematics here. From this relation, nu is equals to 1 minus E upon 3k. So, E is divided by 3k and then 1 minus E upon 3k is equals to nu. This is simple mathematics. So, again rearranging, nu is equals to 3k minus E is equals to 6k, as the Poisson ratio for any material will have the same value. So, from the equation number 3 and 4, we can equate the left hand side of these two equations. So, if we equate, so E minus 2g upon 2g, from here, this is the left side and this is here. These are the same, as I have already told that this is a material property, and now try to solve it whatever you want. Here, if you solve, you will get a relation. This is just a cross multiplication first, that is shown here, right. So, E multiplied by 6k E minus 2g multiplied by 6k. So, this is 12gk, and similarly 2g multiplied by 3k, this is 6gk and minus 2g, and further if you solve it, you will get 6k plus 2eg is equals to 18gk. This is simple mathematics, nothing else. So, you can take 2 common from the left hand side, you will get this result. Now, 2 will be equal to 9. So, 3k plus g is equals to 9gk, we will get in the next step, that is E multiplied by 3k plus g is equals to 9gk. So, what is the relationship between EGK is E is equals to 9gk upon 3k plus g. This is our desired relation. We can use any place for the same material. If two constants, modulus of elasticity and bulk modulus, are known, we can easily find out the value of modulus of rigidity. Modulus of elasticity and modulus of rigidity is known, we can easily find out the value of bulk modulus, and we can use these constants as per our requirement in our analysis. So at this point, our derivation relationship is over. Now we move to the next step for the application of the relations and to determine the values of the elastic constants. So we will attempt few numerical problems based on this modulus of elasticity, modulus of rigidity, modulus bulk modulus, and Poisson ratio. So first problem is determine the Poisson ratio and bulk modulus of material for which Young's modulus is 1.2 into 10 to the power 5 Newton per mm square. This Young's modulus is E. We will write this is E. Young's modulus means here we will consider this is modulus of elasticity, and modulus of rigidity is 4.8. This is G. G is given, and now you have to find out what is Poisson ratio. So we will attempt this problem step by step. So what we will do first, we will see what is given. I have already discussed, that is Young's modulus is given, modulus of rigidity is given. Now we need to find out the Poisson ratio. So what should we do? We should use the relationship between modulus of elasticity and modulus of rigidity. That is E is equals to 2G1 plus nu. So in this equation from the problem, E and G are given. Nu easily can be determined. So to determine Poisson ratio nu, the solution is very simple. E is equals to 2G 1 plus nu. What we need to find out? We need to find out this nu. This value and this value, these are given here. So put the values here. You can find out the value nu. Nu is equals to 1.25 minus 1 is equals to 0.5. This is a very simple problem. We move to the next problem. In the next problem, a tensile test was conducted on a mild steel bar. The data is given as diameter of the steel bar D is 4 centimeter, gauge length of the bar is 22 centimeter, and the load at the elastic limit is 250 kilonewton. Extension at a load of 160 kilonewton is 0.235. Here this load is less than this, so definitely the loading is within the elastic limit, and the bar is subjected to follow, or Hooke's law will be valid up to this 250 kilonewton. Then maximum load which we can apply, that is ultimate load 390 kilonewton is given. Total extension is 70 millimeter up to this, and the diameter of rod at failure is 2.35 centimeter. Then we need to determine the Young's modulus, that is E. We need to find out what is E. The stress at the elastic limit, that we need to calculate sigma E. The percentage elongation and percentage decrease in the area. These four things we need to calculate from this data. So it is given the initial diameter is 4 centimeter, will be converted into millimeter, 40 millimeter. Gauge length is given 22 centimeter, so it will be 220 millimeter. Elastic load is 250 kilonewton, that is 250,000 Newton. Then the load 160 kilonewton corresponding to this load. This deflection of 0.235 mm is given. Ultimate load is given 390 kilonewton, that is 390,000 Newton. Delta F, that is total deflection, is 70 millimeter, and final diameter where it got fractured, DF is 2.35 centimeter or 23.5 millimeter. So here you can notice that I have converted the units what is required. We use Newton and millimeter. So when we write the units of modulus of elasticity, modulus of rigidity, bulk modulus, these units are normally popular units are megapascal, gigapascal. So Pascal is Newton per square meter or megapascal is Newton per mm square. Directly, if I get the answer in Newton per mm square, 1 Newton per mm square is 1 megapascal. So it will be helpful. So I just converted the diameters and the length in millimeters and loads in newtons here, so that I will get the answer in Newton per mm square. So Young's modulus E, we need to find out stress at elastic limit sigma E, percentage elongation, percentage decrease in area. So first step to determine the Young's modulus E within the elastic limit, Hooke's law is valid. Hooke's law is valid, means sigma is directly proportional to epsilon, and sigma is what? Load upon area. So load upon area is directly proportional to delta upon L. It will come P upon A is equals to E into delta upon L. This E is proportionality constant and known as Young's modulus or modulus of elasticity. Here, what is E from this formula is PL upon A into delta. This is the expression we have derived. Here, we can get what is P given here 160 kilonewton. If I consider L is the length, at this, what is the length, area, original area, and what is deflection. So we will find what is given and what we need to determine to apply this formula to determine this modulus of plasticity. So putting these values in expression 1, so the values are given on the at the point of 160 kilonewton. So corresponding to 160 kilonewton, the gauge length is 220 millimeter. So P is 1,60,000 Newton. This is in millimeter. Area, the diameter is given this 40 millimeter. So pi by 4 into d square is the area, and the extension or the deflection at this load is 0.235. It is given, and now you can perform this dimension analysis. You will get this is in Newton, this is millimeter, this is millimeter square, this is millimeter. So this is Newton meter millimeter upon millimeter cube. So result is this, and the calculated value is this 1,19,196.89 Newton per mm square. This Newton per mm square is equals to megapascal. So we can convert it into gigapascal. So modulus of elasticity is 119.198, 119.197. I should make it correct. It should be 7. This is 6. So when I make it round off, so it will increase by 1. So it will be 119.197 gigapascal modulus of elasticity we have determined. Now the determination of stress at the elastic limit. So for the determination of stress, we are having PE, the elastic load that is given. So we will again use Hooke's law. According to Hooke's law, sigma is equals to E into epsilon. E is the modulus of elasticity, that is a property of material. So we have already decided that it is 119.197 gigapascal, and for the remaining part of this solution I will consider this is, or I will assume this is 119.198 gigapascal, because there is a typing mistake, and I have taken this value in fact for the further steps. So we can change the answer accordingly if I take this as 119.197. So according to Hooke's law, sigma is equals to E epsilon, and sigma is equals to P upon A naught. Here A naught means this is original area, and E into delta upon LG. LG is gauge length. Delta corresponding to corresponding to elastic limit we must know, right? Or the epsilon. Epsilon is the, the strain is known, and we have already decided this elastic point. So at the elastic point, sigma E is equals to E into epsilon. Either we have the epsilon or we must have the delta. We must have this delta or the epsilon. This will be our approach to this. At elastic point, load upon original area is equals to E into delta E upon Lg. So these are the mathematical model for the determination of E. Now this is PE upon A naught, that is corresponding to elastic limit, and E delta E upon Lg. This is sigma is directly proportional to delta E upon Lg, or sigma is equals to E into epsilon. Delta E upon Lj is the epsilon at the elastic point. Similarly, P upon A naught at any load P, that is given 160 kilonewton. At 160 kilonewton, delta is the deflection, right? So up to elastic limit, there is a linear relationship, at least proportionality limit. It is a linear relation. So we will get from this relation. So we can find what is the delta E, because delta E is not given in our problem statement. So we need to determine delta E first, and then we will be able to find out sigma. So by dividing this is expression we have. So delta E is nothing, PE upon P into delta. Delta is corresponding to P. This is the deflection corresponding to P. So values of P and P are known, are given in our problem. So delta E, we put the values. The PE is 2,50,000 Newton, 250 kilonewton. P is given 160 kilonewton, that is 1,60,000 Newton, and delta is 0.235 mm, corresponding to 1,60,000 Newton. So what is deflection corresponding to elastic limit, and this is the deflection at elastic limit, value is 0.3671875 mm. So we can calculate the strain at elastic limit, that is equal to the deflection at elastic limit upon original value or the gauge length, So we just put this value, we will have the elastic strain or strain at the elastic point, that is 0.001669. Now we can apply this sigma is equals to E into epsilon to determine the stress at any point within the elastic limit. Hooke's law is valid up to the elastic limit. So elastic limit epsilon is available. We E have already determined. So according to Hooke's law, sigma is equals to E epsilon. This is sigma E at the elastic point, E into epsilon. Values put again. This should be 7. Now multiplied by 10 to power 3 is megapascal, multiplied by 0.001669. So what should be the unit for sigma E? The answer will come in megapascal or Newton per mm square. The product will result into 198.94 megapascal. So we have decided what is the stress at the elastic point. Now we move to the third part, determination of percentage elongation. So percentage elongation is LF minus LG upon LG. LF is final length, LG is the gauge length. LF is the length at the time of fracture, a final length. So it is given the final deflection is 70 mm. So LF will be gauge length plus delta F. So LF minus LG is nothing but this is delta F. We have used this delta F here divided by LG into 100. So 70 upon 220 into 100. This is the percentage elongation of the length of this bar under this loading condition. Now the percentage decrease in the area. For percentage decrease in the area, we must have the final area and the initial area, then the difference upon the original area into multiplied by 100 is the percentage decrease in the area. So final area is pi by 4 into df is square, and df is given, df is final diameter, that is at the point of fracture. So pi by 4 into 23.5 square, value is 433.736 millimeter square. Then initial area is pi by 4 di square. So this is pi by 4 into 40 square. 40 millimeter is the initial diameter, so it will be 1256.637 millimeter square. So the change or decrease in area, AI minus AF upon AI. We can write this AF minus AI upon AI. Normally we write the final minus initial is the difference, so you can use, but in that case the answer will be negative. Negative sign will indicate that is the decrement in the area. Here I ignored the sign to get a perfect positive sign. I consider the larger value first minus the lesser value. That's why I write this AI minus AF upon AI. So I put just the value multiplied by 100, and the decrement in the area is 65.48%. So this area, this is over. In the next lecture, we will try to attempt few more problems on the same topic. Thank you very much.